Problem number 17. Let W3 be this region right here. Integrate negative 3xy, 2x squared z squared over the boundary of W3 with outward normal vector. Again, just like in the previous problem 16, we should be thinking about divergence theorem. So if S3 is the boundary of W3, the integral over S3 of F dot n d sigma, that's the flux integral of f over the boundary here, is equal to the triple integral over W itself of the divergence of F dv. So the divergence of f is going to be the x partial derivative is negative 3y. The y partial derivative is 0. The z partial derivative here is 2z. Okay, so this is what the function we need to integrate here is. What's the region? It's the top hemisphere of radius 1 here, so we should be switching to spherical coordinates to do this integral. And this is not a spherical parametrization problem. It's not doing that. You'd have to do spherical parametrization for the boundary, if that's what the problem is asking you to do. But instead, all we have to do, this is a chapter 15 problem, a triple integral in spherical coordinates. So what do we do here? What are the bounds? The bounds need to be on phi, theta, and rho. It's a sphere of radius 1, so rho runs from 0 to 1. The only bound here in terms of x, y, and z is greater than or equal to 0. That gives us phi is from 0 to pi over 2. Theta runs from 0 to 2 pi. So it's the integral from, let's see, phi from 0 to pi over 2, and theta from 0 to 2 pi. Rho from 0 to 1 of negative 3 times what's y in spherical coordinates, rho sine phi sine theta sine phi, plus 2 times what's z in spherical coordinates, rho cosine phi. Don't forget the rho squared sine phi, d rho, d phi, d theta, d phi. Okay, in the interest of time and sanity, I'm not going to evaluate that integral, but straightforward triple integral to evaluate.